Hi there, I'm looking at doing a couple more questions from the homework. First off, on page 147, question 40, is the person pulling the ducks, right? And it says in question 39, the person has two ducks, right? One of the ducks is the 2 kilogram duck, and one of the ducks is the 5 kilogram duck. I've drawn them as boxes because I don't do ducks very well. Then question 40 says, if the student in problem 39 receives an extra duck, which is 1 kilogram, and he puts the new duck at the front of the row, so here's my new duck. Question is, what is the acceleration? So very similar to what we had done before, I'm looking at the fact that if this is all one thing, right, it's going to accelerate together under the net force. Because they're not separate, they're one basic kind of solid continuous mass. So if I basically look at this question here, I can say, what is the acceleration? I know that the acceleration of this one will be the same as the acceleration of this one, which will be the same as the acceleration of this one. They're all going to accelerate together. So if I include all of them as a single free body, then I can now say that F net equals ma, where the F net is my 10 Newton force. The mass is 5, 6, 7, 8 kilograms. And the acceleration turns out to be 1.25 meters per second squared. And the direction is in the direction of the applied force. Now it says, what would be the tension in the string between ducks 1 and 2 and between ducks 2 and 3? So like before, if I call, let me get rid of this one. If I call this T1 for first string, T2 for the second string, and T3. So for part B of the question, it's saying, what is force T2? Now, I can look at this in two ways. I can draw a free body diagram around all of this stuff here and say all of this 7 kilograms is being pulled by T2, or I can look at this one here and say T2 is working on that one too. So it doesn't matter which way I work on it. I'm going to choose the other way. I think it's probably a little bit easier, but it gives you the exact same answer. Right, so if I say, what is T2 doing? Well, T2 is the only force that's pulling on that 7 kilograms worth of toy. So if I was to redraw the free body diagram, the free body diagram would be the 7 kilogram toy with lots of wheels being pulled forward by the string with undergoing, T3 actually, undergoing T3. No, I'm sorry, T2. Darn it. Okay, T2 is pulling everything. I just got to slide my picture back down so I can see it. Okay, so T2 is pulling all 7 kilograms. And what do I know? Well, the only force that's acting on this whole system, F net, is the force from T2. That's F net. And that's also equal to ma. And I know that I'm accelerating 7 kilograms. And I already know the acceleration is 1.25 meters per second squared, so I can calculate F2 now as 7 times 1 1/4, and I'm getting 8.75 newtons. Now, I could do this the other way and say, okay, let's look at this object here and say, what are the forces acting on this one? Well, I know that there are two forces acting on this 1 kilogram mass. Now, the 1 kilogram mass is being pulled forward by T1 and back by T2. So let me roll this up here. So here's my 1 kilogram mass being pulled forward by the first string and pulled back by the second string. Again, remember it's T2 that I'm trying to solve here. It should turn out to be 8.75 newtons. Now, if I say, what is going on with this particular toy? Well, if I was to draw the F-net, or write out the F-net statement, F-net says there are two forces acting here, T1 force and T2 force. And the F-net, we know is MA, and we know that T1, given in the question, is 10 newtons, and T2 is unknown. Now, if I keep on going here, I know that the mass is 1 kilogram, and we know that the acceleration is 1.25 meters per second squared. Ten goes across to the other side, and I end up with T2 equals negative 8.75 newtons. Now notice that I had 8.75 up here, and I have negative 8.75 down here. The force in a string can never be negative, right? So the amount of tension in the string, remember the purpose of a string is to change the direction of a force. It's actually going to apply an equal force at both ends of the string. So if it's pulling with 8.75 at one end, it has to be pulling with 8.75 at the other end, but I would never say that a string has negative force. It's kind of like pushing on a string, right? And that doesn't really make sense. So when we're talking about strings, we use the magnitude of the force, which in this case would be 8.75 newtons. Now if I move down, so you can see it doesn't matter where in that original picture I look at T2. I can look at T2 as it applies to the reverse, the back part of the toy. I can look at what T2 is doing to the front part of the toy. And both of them give me the same answer for T2. The last part of the question, C, says find the tension in the string connecting the ducts between 2 and 3. All right, so again, I'm just going to draw a free body diagram for duck C here, the one at the end of the toy, being pulled by T3. Whoops. Okay, so here's my last part of the toy. It is 2 kilograms being pulled by T3. Okay, there's my free body diagram. So if I say, what are the forces that are acting here? There's only one. I don't know what it is yet. The F-net is MA. The mass is 2 kilograms. The acceleration we've already used a bunch of times is 1.25 meters per second squared. And I know therefore that T3 equals 2.50 newtons. And again, I could work backwards. Part D says to do what I just did with the other question, which is to analyze T3 from the other side. You may want to try that on your own just for practice. And what you should be able to show is if you analyze T3 from this side, from this side here, you can show that T3 is pulling back on the rest of that toy. I know it's pulling back because if I snip T3, the toy will weigh less and will accelerate faster. So what is T3 doing? It's pulling back on the first part of the toy and keeping it from accelerating at a faster rate. Okay, so there's question 40. Now, I was also asked to do 50, part B, and 52. I did 52 in my lesson this morning, so I'm not going to do it again. But for 50, page 148. Question 50's got a person sitting on a sled. We're told the person and the sled have a combined mass of 110 kilograms. So here's my sled. Here's the person sitting on the sled. It says there are two people applying forces to this one. The first one is pulling with a force of 40 newtons up 20 degrees right. So there's up, and there is my 20-degree force, and it's probably somebody walking along here with the rope over their shoulder pulling the toboggan. And then I also have a person who is back here who is pushing on the person's shoulders as they're sitting there, applying a force down 75 degrees right. Down 75 degrees right. So there's the force from the back. That force from the back is 44 newtons. Let's make this longer. So this person at the back is pushing down and pushing forward. The person at the front is pulling up and pulling forward. So I'm going to analyze these two. Actually, I'm going to redraw that one vector down here. There's my 20-degree angle. There's my 40 Newton force from the person at the front. And now I'm going to analyze those two vectors in terms of SOHCAHTOA. So if I solve for this side, which is on over here, the F down is equal to, so there's my 75-degree angle. It's 44. That's the adjacent side to the angle, so it's cosine. 44 cosine 75 degrees. And the bottom, the force this way, is going to be equal to 44 sine 75 degrees. Okay, so if I analyze my two forces, 75 cosine times 44, I'm getting 11.4 newtons down, and I'm getting 75 sine times 44, I'm getting 42.5 newtons that way. Just double check my math. Okay, if I look at the other force, the other person's 40 Newton force, I have a force up, which is equal to 40. There's my 20-degree angle in there. So it's adjacent to the 20-degree angle, so it's cos 20 degrees, cosine of 20. So my force up is 37.6 newtons. And my force this way is equal to 40 times the sine of 20 degrees, because I am opposite to the 20-degree angle there, and I'm getting a force which is 20 sine times 40, giving me 13.7 newtons. Okay, so the question is asking now, calculate the acceleration of the person in the horizontal direction. So as they pull on the toboggan is going this way. Right? So I'm going to ignore the up and down forces and only look at the forces that are in the plane of motion, which are this 42.5 newtons here and this 13.7 newtons here. So my total force in that direction is 42.5 plus 13.7, which equals 56.2. 56.2 newtons that away. And I know the mass of the toboggan. This is the total or net force acting, because all of my up-downs are canceled. The toboggan isn't going up or down, which means there is no net vertical force. I only have a net horizontal force, so the net of all the forces is that horizontal piece, which is the 56.2 newtons. I know the mass of the toboggan and the tobogganer are 110. So I know the acceleration of the toboggan and tobogganer are 0.51 meters per second squared. Okay, so that's the A part of the question. The B part of the question says, if the person and the sled experience a force of gravity of 1078. Okay, so let's go back here for a minute, and let's just say I have to add another force here now, which is Fg, which is 1078 newtons. So there's the downward force. So the question now becomes, how much more lifting force is required by the person at the front in order to balance the weight of the sled and the person? In other words, to lift, to be able to zero the vertical forces, the downward forces. So if I look at the forces that are acting here, I have a downward force of 11.4 and a downward force of 1078. So 11.4 and 1078. And I also have an upward force of 37.6 newtons here because of this component of my person who's pulling at the front here. Right, so that's 37.6 newtons. So the question is, how much more force would the person require in order to balance the weight of the sled and the person? So again, this is really not a good question. It's not worded very well, and it doesn't really make a lot of sense. But I'm basically thinking it must be asking me for what missing force here would balance all of the downward forces. So if I look at the fact that I've got 1078 and 11, 1089.4 down, because of the person pushing on the shoulders of the tobogganer and the planet pulling down on the toboggan and the tobogganer. And I see an upward force here of 37.6. This has got to be 1089 minus 37.6. And I'm getting 1051.8. Okay, it's saying that I need to have an additional 1,051 newtons in the upward direction. I'm just going to double check that that's the answer, because like I said, the question is not especially well worded, and it looks like they're not even giving you chapter 4, question 50. 0.56 meters per second squared. No, that's not even a possibility. 56. Okay, so the answers in the back of the book are really not looking especially helpful. So those should be the answers. Well, those are numerical, end of chapter. Yeah, that should be the answer there. Yeah, so they haven't given us an answer. So I'm assuming that this is what they're looking for in terms of, again, one more time, if the person and the sled experience, how much more lifting is required by the person pulling at the front of the to balance the weight of the sled and the person. All right, so I'm assuming that that's the answer they're looking for. So again, not a great question, but sometimes you just have to try to imagine what exactly could that possibly mean, right? And that would be my answer. All right, so I will leave that for now. Hopefully you get these answers, and hopefully your studying is going well. Again, for tomorrow's tests, don't be late, because I'm going to open the questions at 9, and I'm going to shut them down wherever you are at 10:15, or I'm going to open them at 7 p.m. and shut them down at 8:15. All right, so I will give you the 15. Oh, you know what? Did I say this morning I was going to give? I think this morning I said I was going to give 90 minutes. So if anyone was having connectivity issues, because I was having connectivity issues this morning, I'll give you the full 90 minutes in case you need the extra time because of computer stuff or whatever's going on. All right, but hopefully it won't take you that long. And if you've seen the layout for the test online in the announcements section, then you'll know that it shouldn't take you that long. Time yourself when you're doing it so that you don't spend more than 15 or 20 minutes. So there are 2 quizzes. One is the non-calculation part, worth about 15 or so marks. The second is the calculation part, worth most of the marks, worth probably 45 marks. But even though it's only 15 questions, I know I said 10, but some of these are like that question 50 there where there's an A and a B. So instead of asking you for a magnitude of the force and a direction, I've asked, like, question 9 is what is the magnitude of the force, and this question 10 is what would have been the direction for question 9. So again, leave yourself lots of room on your paper, because that's going to be your way to monitor what's going on, and maybe go back to it if you have time at the end, or if you want to double check your answers. So give yourself lots of time, give yourself some working space, get your calculator ready and everything, and I'm assuming that you should all do very well on this test. All right, take care. Bye for now.